All right, guys. Welcome to our second meeting where we're going to discuss data parallelism, uh, all everything up to zero. Um, so, um, a quick overview of what we're dealing with. We have a model. We're feeding our model some data. The model does a forward pass, it does a backward pass, it collects gradients, does an optimization step, and then we get an updated model. And to speed things up, we want to run everything in parallel on multiple GPUs. And when we talk about data parallelism, we mean that we deploy the model as a whole, like a whole model on each GPU. And then um, for each GPU, we feed different batches of data. Uh, each GPU independently does a forward pass, does a backward pass on its own batch of data. Then we kind of accumulate all of the gradients on each GPU, do the optimization steps in parallel once again, and we get back the updated model on each one of the GPUs on all of the collected gradients. And this way we can kind of parallelize, well, it's data parallelism. So we parallelize what we feed to our GPUs and get to kind of split our very, very large batch in multiple mini batches. And each one of these mini batches gets its own GPU to execute. Um, and one thing that I'd like to highlight is that let's go back for a moment. So once we did a backward pass on each one of the GPUs, each one of the GPUs has its own set of gradients. And now we need to kind of uh, distribute these gradients between each GPU. So for instance, when GPU 0 has gradients for GPU 0 only, we want to send these gradients to GPU 1 and GPU 2. We want to send gradients from GPU 1 to GPU 0 and GPU 2. And we want to send gradients from GPU 2 to GPU 1 and GPU 0. So in the end, each one of the GPUs is going to have all of the gradients accumulated. And then each one of them can individually and independently do the optimization step and get the updated model. And this operation is called all reduce. So basically on node 1, this is our GPU 0, GPU 1, GPU 2, GPU 3. We have different data sets, and we kind of distribute these data sets in such a way that all of the nodes, all of the GPUs in the end have all the data. And when we look at the timeline of the execution, we do the forward pass. And I think that here it's like the picture is not very accurate. As far as I understand, when they show 0, 1, and 2, they mean like first layers, mid layers, and last layers. It's just like they didn't like have enough space to fit all of the real number of layers, which could be many, many more. It's just an example. So we kind of do the forward pass. We do the backward pass. And remember that it happens in parallel on all of the GPUs at once. And then when we do this all reduce, all of the GPUs are waiting. They were wasting computation cycles. And once this all reduce happens, finalizes, we do the optimizer step and we start the cycle all over again. And yeah, just what I've covered, that this optimization step happens on all of the GPUs at once on the same accumulated gradients. But the real problem lies here. Real problem is that once we finish the backward pass, now we're waiting for this all reduce operation to complete. Yeah. Each GPU needs memory for all gradients. Oh yeah, that's another thing to remember, that they didn't explicitly mention it in a book, but it kind of came to my mind that to do this all reduce operation, we we need memory to collect all of the gradients, right? Unless we kind of calculate averages as soon as the gradient arrives from the other set of GPUs. But nevertheless, there's got to be some sort of a memory overhead once we receive a batch. Once we receive a batch of gradients from other GPU, we need to store it somewhere. So just keep in mind that there might be some memory overhead, at least to my best understanding. And the first idea of the optimization that the book proposes is that we can start sending the gradients for each layer one by one. If we go back to the original picture, I'm not sure if I have it in my slides. Nope. If we go back to the original picture right here, we have multiple layers, right? So when we do the backward pass, we start with the last layer, then we go to the layer last minus one, layer last minus two, and etc. and etc. But when we go to the layer last minus one, we already have gradients for the last layer. And this is exactly what the book proposes, that when we have gradients for the last layer, send them over straight away. So do this all reduce operation on the gradients only for a single layer. And then when we calculate the backward pass for the layer last minus one, we we calculate the gradients for the layer last minus one when we do all reduce for the last layer, and then when we calculate the gradients for the layer last minus two, we do all reduce for the layer last minus one. And this is what is kind of depicted here, that we have all these boxes for step two, then we have all these boxes for step one and step zero. And what kind of made me scratch my head is that we have multiple boxes for step two, but we have only like one huge box during the backward pass for this step two. And once again, to my best understanding in this book, they just it's a bit of poor visualization. So what they meant by 0, 1, and 2 is that like the first group of layers, mid layers, and last layers. In reality, it means that it's probably not 0, 1, and 2. It's like 0 to 5 or 0 to 10, then 10 to 20, then 10 to 20 to 30. So like first layers, mid layers, and last layers. And this is what all of these looks like. So basically, we kind of do this summation operation across all of the nodes, and then we calculate the average because we know upfront I think this CP/DP world size, it's basically the number of data parallelism units, so number of our GPUs. So the next optimization that they propose is that instead of sending these small gradients one by one for each layer, let's accumulate these gradients in some sort of a chunks. So for instance, let's accumulate the gradients for the last layers, final layers. Let's accumulate the gradients in a batch for mid layers and create a batch for the first layers. And this way we get a bit of delay, like this white space after the backward pass to communicate the last batch of gradients. But it turns out that communicating single large units, fairly large units, it's much more efficient than communicating multiple small units, especially when you have many GPUs. So this is what happens instead of multiple gradients for last layers, only one huge chunk. But mom, what if my batch size is not big enough for optimal convergence? Well, when we didn't do data parallelism, we could do gradient accumulation, right? It was discussed in the previous chapter that When we do backward passes, we can actually do multiple backward passes, and then we can accumulate gradients, and then we can do optimization step on the accumulated gradients. So the authors of the book, they propose to do the same thing, but in this distributed setting. So on each GPU, independently, we do this gradient accumulation. And then we hit the last cycle of the backward pass. At this point, we start doing this, well, basically what we discussed before. When we accumulated gradients for the last layer or for the multiple last layers, depending on how we go about it, we send that chunk straight away and we keep accumulating the gradients for other layers as we go back through our model. And then once again, we do optimizer step on all of the GPUs at once. And the last thing that they wanted us to discuss, or at least take a look at, is that now our batch size, it's kind of global batch size. So global batch size means like number of data sequences, data items that we process in parallel across the entire cluster of GPUs. And the equation is like mini batch size, stuff that gets onto each one of the GPUs, multiplied by gradient accumulation step, number of gradient accumulation steps, and multiplied by the data parallelism number, which is the number of our GPUs. And the final recipe that we have so far for training is to find the best global batch size in tokens. Somehow, like sacred empirical knowledge, you should either do your own experiments or get it from literature or whatever. Then find the best sequence length. Once again, some sacred empirical knowledge, generally 2 to 8 key tokens. Find the maximum local batch size on a single GPU. So that means we kind of feed the model on a single GPU, and then we see how much space we get left after fitting the model to store the actual sequence and to do the forward pass and to do the back propagation. And this way we get our MBS from this equation. And once we have MBS, and we have this GBS, global batch size, we have mini batch size, we know our DP, it's the number of our GPU units. We can easily calculate one missing variable, which is our gradient accumulation, number of gradient accumulation steps. Now this is exactly what's proposed. We have the number of GPUs and we calculate the remaining number of gradient accumulation steps. One thing to note is that we can't infinitely scale our pipeline with GPUs. So each bulk of new GPUs has diminishing returns. So for instance, this is the graph that they have for some unknown GPU and unknown kind of data, but I think that it still could be applied for like the trajectory with a few caveats, and the constant change should be the same for pretty much any GPU and any kind of data. And as we can see that with each increase in the number of GPUs, we have diminishing returns. So for instance, when we increase the number of GPUs from 8 to 16, we observe already at this small scale, we observe a slight drop in throughput in tokens per second per GPU. And that means that with each increase, with each subsequent increase, each one of the GPUs is going to process less and less tokens per second. And to my understanding, it happens because of these overheads to communicate with the GPUs. So when we hit like some large number of GPUs, like 500, 1000, and many more, it seems that at that point, a lot of resources and a lot of time is wasted on the communication between GPUs instead of on computation of gradients. And well, so far we've been discussing how to scale our training when we can fit our model on a single GPU. But what if our model is very, very large? So for instance, in the book, we see that for 8 billion model, uh, I think on the x-axis, what could be on the x-axis? I think on the x-axis is the sequence length probably. So 8 billion model for the sequence length of 16K is already like for 150 gigabytes. But if it's a 70 billion model, even like for very short sequences, we don't have any memory left for gradients, for activations, and etc. etc. We only have memory. So like this blue stuff is memory for all parameters, and I believe that pink is well, what could that be? I don't think it's gradients. Activations are orange, optimizer, something else. Who knows? And to discuss what to do when we can't fit a huge model on a single GPU, join us next week and read the next chapter. So this is it from my side. Do we have any questions? And sorry, I can't see hands, so just speak out. Speak up.
No questions?
You had this place earlier in the slides where you said you didn't understand something. Can we take another look at it now?
Which place?
I forget now what you said that wasn't clear to you immediately in the beginning.
Okay, let's go through the slides.
Sorry.
Stop me.
Yeah, I think I remember now. I think it was about the memory overhead. When you did
Yeah.
you're saying when
So
you did the L reduce, then there must be a memory overhead.
yeah, I think a little bit of memory overhead, right?
Right.
Because like when you receive a batch of gradients from the other GPU, you have to store it somewhere before you do all the computation, right?
I guess you can be like smart enough and kind of do in place summation, and kind of almost not use any extra memory.
Yeah, but how? Like you say,
Uh,
you receive the batch of data at once. Do you think like you receive like
no, you have your own batch of data, right?
yes, and
Which
you
you're
receive
about to
another
send to
batch of
everyone else,
data?
and you receive like 3 other batches of data from your neighbors.
Yeah.
And I guess yeah, there is like at least one maybe extra copy needed, but
Yeah,
you
one well
immediately
in
like
another batch, right? At least one other batch.
yeah, at least one. I guess you're right. Unless maybe there is um fair
I
point.
would guess that when you are doing like aggregation between GPUs, you're vastly limited in terms of memory bandwidth between CPU and GPU. So you're receiving all of your parameters, like all this aggregation data you're receiving in RAM. So you do not need a lot of VRAM to add the summation because basically you like just adding two matrices is the worst, close to the worst things that you can do on GPU. So uh, it does not really matter, and like the limiting factor there is just PCIe throughput, I would
Do you
say.
think? Like based on the picture, like based on they
I was kind
say
of under
that
impression that sorry, go ahead.
yeah, we do all reduce. That means that we kind of get all of the data on each one of the GPUs. So like I don't think anything is computed on CPU at all.
Yeah, there is like a thing called NVLink where I think you connect GPUs directly over the network and like it bypasses the CPU and RAM entirely.
Yeah, I
No,
think that's the whole idea, to kind of bypass
yeah.
any CPU overhead, because that would be extremely slow to kind of
I mean, you
go
can do
around.
it. It's probably doable. It's just, yeah, not practical.
Oh, yeah, again, like just adding two matrices together, like it's limited by how fast you can load a new matrix on the GPU from through PCIe, and even through the NVLink. Again, you're limited by the memory bandwidth within the GPU.
Yeah.
So you can basically like this addition can be uh, paced out with the how fast you are uploading the data. So, and again, it's a lot slower than the actual tensor multiplications or anything else. So you do not need to have the full data from the other GPUs at once in GPU. So it's probably
Well,
not
not from
possible.
all the GPUs, but probably from one GPU, like one batch of data, right? So some overhead is still
Well,
there.
you can slice it probably. I have no idea how it is implemented, but again, like it doesn't seem like you would benefit from uploading the full like full gradients from the other GPUs into VRAM and adding them together. So you can
Um,
just slice it probably.
yeah, but I mean that would require some pretty sophisticated slicing, right? Because then you need to send the data. I don't even know how GPUs communicate on lower level, to be honest. It's like, what kind of protocol is there? Is it like, do they, is it always an order delivery? Can it be out of order? Because the only way of how we can get almost zero memory overhead is that when we send the chunk of data from one GPU to another, so the chunk of data that we send, it's always guaranteed to be in order. And then the bytes that we get, well, we know straight away. So these bytes are probably from the, it's the tensor for a single layer, and then we can average it immediately as soon as it arrives. So it's kind of some kind of streaming data, streaming based computation. But based on the code that I see here, I don't think. Yeah, well, this code doesn't really tell us all. Tell us much. It's dist-all reduce and what happens under the hood of this dist. Okay, yeah, it might be some kind of streaming-based stuff, maybe. Does anyone know?
I know one algorithm which is called ring all reduce. It's a bit funny one that basically you imagine a ring made of GPUs, like they all kind of stand in a horovod. And then what happens is each GPU receives copy of gradients from the right neighbor, so adds its own copy, and then passes it to the left neighbor.
Yeah, I think it's been discussed somewhere in the book. I didn't.
Yeah, maybe later it is. And then after
Okay.
like n steps of that, everyone has a copy of all weights, and then they can sum up in the aggregation.
I have a picture for it somewhere. Give me a moment. So they inside of the book in the appendix they actually have crash course. All right, I'm ready to share. So sharing. So this is what they have for the ring all reduce. So we have like an array or a tensor, doesn't really matter, right? Okay, so it says that the first animation shows reduce scatter altogether. Yeah, I think probably I need to read it offline. To be honest, I don't really, I can't really comprehend on the fly. However, like ring will reduce, it's like two key steps, reduce scatter and altogether. So first, we kind of get this guy here. We get all these sums, and then what this altogether does.
You see how it's all like in place sums and there is no memory overhead seemingly.
Yeah, okay. Oh, okay, so kind of they get the diagonal stuff. So right here, when they send it one by one, they get the diagonal stuff, right? So you see, like right here, they get the uh, across all of the GPUs, each one in one of the chunks, they have all of the sums on the diagonal, and then they kind of distribute the diagonal stuff down down to all other GPUs. Pretty cool. Right. Any other questions?
Yeah, I think the NVIDIA library, like I think a CCL library that is basically is aware of the topology of how your GPU are connected together, and will send like maybe it won't make a ring, it will maybe make a tree out of them, and it's like tries to adapt it to the topologies that you have.
Cool. Well, awesome. Then thank you all for coming and see you next week. That was short, much shorter than last time, probably much less entertaining, but hopefully when we get eager to present again, we'll get back our awesome presentations.